So in this video, we're going to fill out what I'm going to call an acceleration table. The different columns just denote different quantities. The first column is just telling us how much time has passed. We're going to start at 0 time. What 0 time means is 0 elapsed time. There's no such thing as 0 time, but there is such a thing as no time passing. So it is the instant that we start our stopwatch. We're going to say that we have an initial velocity of 100 meters per second, and so that's why this quantity just follows through the entire time. In this example, we're always counting our initial velocity as the velocity when no time has passed. We have a column for our final velocity and our average velocity, as well as our initial starting displacement, which in this example is going to be 0 meters. Our final displacement meaning after 0 seconds have elapsed, what is our final displacement? After 1 second has elapsed, what is our final displacement? And finally, we have a column that denotes our acceleration. In Regents physics, we are always going to deal with a constant acceleration that may be 0 or non-zero. In this case, it is non-zero. The negative of this acceleration simply means it's in the opposite direction as our positive starting velocity. Right now, this positive and negative can't tell us which direction we're moving in terms of north, south, east, west, up, down, or left and right. It simply tells us that they are opposite directions. Now, I know I said that we don't know which direction this object is moving, but let's just pretend that we know the object is already moving to the right. Again, it has an initial velocity of 100 meters per second at time equals 0 and a displacement of 0 at time equals 0. What this means is that whenever I decided to start my stopwatch, the instant I started my stopwatch, it read 0 seconds. I decided to call wherever this object was, the instant I started my stopwatch, 0. I decided to call it 0 because that's where I decided I wanted to measure from. Okay? So the first quantities we're going to go ahead and fill in are the final velocities. At time 0, when I started my stopwatch, it was already moving with 100 meters per second. Since no time had elapsed, its final velocity was still 100 meters per second. What you'll notice is that after 1 second, it decreased its velocity by 20 meters per second. This is the acceleration. Acceleration means the rate at which we are changing our velocity. In this case, every second we are changing our velocity by negative 20 meters per second. That means when another second goes by, we are again going to decrease our velocity by 20 meters per second. When another second goes by, it happens again, and so on and so forth. I think you can see that as we move down this column, we're simply taking the number and subtracting 20. So that finally, after 10 seconds have elapsed, we've gone from moving at a velocity of 100 meters per second to a velocity of negative 100 meters per second. So we started by moving in one direction. After some amount of time, we actually weren't moving at all. And then we started moving in the opposite direction. Next, we're going to go ahead and fill in this average velocity column. You'll recall that the average velocity, since we're dealing with a constant acceleration, is simply going to be the average of our initial and our final velocities. In this case, we have our column of initial velocities and our column of final velocities, so we're just averaging them. The average of 180 is 90, of 160 is 80, of 140 is 70. I think you can see that we're just decreasing our average velocity by 10 meters per second every time. You'll notice that after 10 seconds, our average velocity reaches 0 meters per second. What does 0 meters per second mean? It means that we're not moving at all. So even though at this moment in time we actually are moving, it's as if from when the stopwatch started, we didn't move. We're about to see what that means. So now we're going to fill in what our final displacements would be. After 0 seconds had elapsed, we obviously were still in the same spot. After 1 second elapsed, we had moved 90 meters. We simply found that by taking our average velocity, which says how far we move every second, and multiplying by the number of seconds that we were moving. So for our next final displacement, which will be after 2 seconds elapsed, we will have gone 80 meters every second on average for 2 seconds, which is 160 meters. And we just fill out this table by multiplying our average velocity by our time. So I'm going to go ahead and just finish filling this out. Now I'm going to pause this because I want you to notice what happens. We're moving forward initially. Okay, we'll call this forward. We'll call this positive forward. And as we're moving forward, we're also slowing down so that eventually we come to a complete stop. So we're moving, we're slowing down, and then we come to a stop. We've reached some maximum displacement from our initial position. And then our displacement shows that we're actually getting closer again, which makes sense because at this point in time we were stopped, and then we started moving backwards. So we started getting closer to our initial position until finally we reach our initial position. We started at this spot right here. We moved, slowed down, stopped, went backwards, and ended up here again. So even though we're still moving when we reach this position, we would find that if we went to 11 seconds, we would be at some other spot. But right now, at this instant, when 10 seconds have elapsed, we're exactly where we started. So our average velocity is 0 because it's as if we had never moved at all.